Ladies and gentlemen, hello and welcome to the KEMET webinar on our KEMET common mode and dual mode chokes for automotive applications. My name is Alexander Nebel and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter is Michael Freitag, our Technical Product Manager for Magnetics. Before we start our webinar, I have some information. We invite you to ask us questions. You can address your questions at any time during the webinar with the chat function on the right-hand side in your browser. We will answer all of your questions at the end of the webinar. Also, no need to take notes. We will publish the presentation afterwards. Hello Michael, thank you for presenting today. Please tell the audience shortly about your role inside KEMET and then you can start your presentation.
Hey, good morning, Alex. Good morning to the audience as well. As Alex said, my name is Michael Freitag. I'm responsible for the product management in Europe for the magnetics, sensors, and actuator business group that we recently have founded 2 years ago. And welcome to everybody. So today, I want to talk a little bit about common and dual mode chokes for automotive applications. Because a recent development in the automotive industry, as you all know, is that e-mobility is picking up. So that means that everything is more or less electrified, what was mechanical before. And so forth, because of the switching environment of the semiconductors behind in the applications, there's of course an increased demand for interference attenuation in these applications. And these chokes I talk today about is more in the range of, let's say, the power environment. So it might be an electronic power steering, it could be an air conditioning system in that high voltage environment. And so let's go through the presentation. Basically, I put a few bullet points together. Starting, of course, with the demand for the EMI attenuation and probably the interference separation to have a better picture about this. Then the basics about the differential, common, and also dual mode chokes that we recently have developed. Then coming to like the behavior of soft magnetic materials, and those were all founded or developed for different areas of application, and I will talk about this. And then also the magnetic saturation has some influence on the performance of the choke, and this already depends on the different materials that could be used, and every application is really different, so you cannot judge before. Then the temperature rise, that is definitely a parasitic in, let's say, unforced air conditions, so without any additional heat sink or air which is kind of going through the application, and then also talking a little bit about the product availability, what we can recommend in this case. So the high temperature common mode chokes, of course, as I said at the beginning, depending on the noise source or the interference source of an automotive IGBT, MOSFETs or other switches which are used, that defines basically the topology of the filtering. Switching frequencies and harmonics, they are really necessary to evaluate what kind of material and what kind of topology is best, how many stages a filter needs, and so on. And it's also about, of course, voltage rise time, or the dV by dt, because as you know, I mean, the latest topologies in semiconductors switching quite faster. That means that also interferences in a higher frequency area will be found that need to be filtered. And that links to the right soft magnetic material. And also, as I said in the beginning, I mean, separation might be necessary to define if there's really what kind of filtering is needed. And of course, there's an automotive demand. Let's say the OEMs, they specify certain limits as well for the lower frequency area, as also for specifically for the area around 100 megahertz. because FM radio is distributed there, and you don't want to have an interference between your air conditioning system and the radio which you're listening to. This is typically an OEM requirement, and as you can see, I mean, there's with a certain kind of choke setup, filter setup before, you will need to get under the limits, and usually in the dominant frequency area, in the lower frequency area, and up to 30 megahertz as well, it's predominantly common mode interference that you found. It's just around the switching frequency, which might be somewhere below 100 kilohertz. There you find also differential mode noise, and of course in a high frequency area, as I said, around the FM radio. What we do, we have also an AMC Engineering in Japan. I mean, the MSC business group is coming from the former NEC Token, nowadays Token Corporation, and we have a lot of experience with measuring also noise, and we offer this service basically globally. However, we have, of course, dominantly Japanese customers which are taking this service into account. And what we did there so far is we built a splitter for the interferences. So the usual view, which you can see on the left side, is containing common mode as well as differential mode interferences. And with this splitter, we can separate both from each other to find the right topology behind how to filter these interferences best. And the outcome is then that we have these two lines basically separated in the spectrum of over frequency. You can see where we need to do some filtering. And then for the synchronous interferences, you either need the common mode choke to attenuate this, or this is also possibly with a Y-cap. And I show you on the next slide also how this usually looks like, or one of the next slides in a schematic. And for the asynchronous noises or interferences, typically is a differential mode choke needed, or an X-cap to attenuate these properly. And this is all come together, of course. You have limits also for leakage, so that means your caps could not be as big as you might need them. So it's always like a gamble between the chokes and the caps to find the right attenuation that is needed. So when we compare differential and common mode chokes, there's some, in the basics, there's some really big differences. A differential mode choke, whatever you do, I mean, you initiate some magnetic flux in the core due to the reason that there's only one copper wiring around, and it is independent. If it is a low or high frequency, you will always initiate this. And that means that with a higher, let's say, flux in the material, that also this material needs a high saturation capability, because if it saturates, it looks like the inductance or also the permeability is going down. So that means in a differential mode choke, it's really necessary to look into these capabilities. In a common mode choke, on the other side, I mean, you have two coils which are wound in the contrary way. That means that all the, let's say, DC and AC, whatever is attached to it, it will not generate from the main frequency or from the direct current magnetic flux. So this is cancelled out. But if you have interferences on both lines at the same time from the same direction, which would be usual for the switching, then you generate a magnetic flux, and this magnetic flux is also, of course, necessary to convert this interference energy into a heat rise of the core, and that means that you kind of reduce the electric energy and convert them into thermal energy in this case. So this is a, let's say, classic setup. So you either have a differential mode choke or a common mode choke. Of course, both have some kind of parasitics And so we talk about what can we do to increase these parasitics to create a new component feature. So again, the common mode chokes are canceling each other out, but what happens if we build in a magnetic path into the topology of this component? So if there's another, if there are this what we usually call the air gap in between, when we lower this and make this smaller, that means that we're increasing basically a magnetic flux around one individual coil, and that means it has differential mode characteristics. And that's also then basically how we create a new component feature, and we call it a dual mode choke and sometimes a hybrid mode choke, because it has a common mode choke as a basic situation, but it increases the dual mode or the differential mode behavior. So that means you may get along without an extra differential mode choke, but have both in the same component. So as I said on one of the last slides, this would be, for instance, a typical noise filter circuit. And it is, of course, there's some capacitors involved as well as some chokes. And in this case, L1 and L2 are a combination of a common and a differential mode choke, while the capacitors, of course, need to be individually here. And it is maybe also plausible when you think about this, that if you have the interferences on both lines at the same time, with, for instance, a capacitor between those lines, you would not really attenuate these interferences, because they are exactly on both lines in the same value existing. While if you take a capacitor and you attenuate this noise or make a, let's say, kind of low impedance towards ground, then you can, from both lines, you can filter that interferences to ground. And that's the same basically when you're using chokes, just in the other direction, as I just explained a few slides before. So how does it look like? I mean, you can see a common mode choke here with like an additional differential inductance for high voltage and also for automotive requirements. And typical examples are varying from like 15 up to probably 50 amps or so. And at 400 volt or 800 volt, here we picked an example for 20 amps and 400 volt DC. So the maximum power of that application would be somewhere around 8 kilowatt, for instance, for a high voltage DC power steering. And the requirement is as well differential and common mode noise attenuation as per the OEM requirement. So on the left side, you see the common mode behavior with around 1.1 millihenry at 100 kilohertz, and you see this, how this varies over the spectrum. And you also can see that above 1 megahertz, this will decline because then the parasitic capacitance of the winding will play a major role, and that will drop your the attenuation in this case. On the right side, there's a differential mode behavior of around 15 microhenry. And this is also a typical example what some people are using in a pure differential mode choke in kind of a value, and it can help to attenuate the noise or the interferences below a certain level. And this series is called SCN. I will show you a little bit about variations at the end of the presentation. And this is kind of a new development with a specifically shaped core in an oval mechanics. And as you can see on the right side, there's a field and a specific magnetic field and flux going through the air, which is better in this oval shape to increase it than if you would have a typical toroidal shape in this case. So what is the next thing is, of course, the temperature requirements for such a component in the application, and the maximum conditions require, of course, a proper selection and the design of all filtering components. Of course, capacitors behavior need to be selected properly, the chokes, but also if it's really necessary to have a higher high frequency attenuation, it might be that ferrites come into play as well, which drop the very high frequency noise below certain limits. And the choke converts the high frequency, as I said before, into core losses that increase the heat of the components, and the impedance and the interference current guide into that power loss that we can't really judge because it's depending on the application. However, when we get like a first idea about the requirements of the customer, we can at least calculate the copper losses, let's say, which is relatively easy to calculate because it's basically the main current that you have, the DC resistance of an individual coil, and then of course times 2 because you have 2 of those in the common mode filtering component. And the example here, which I just chose, is just to give you an idea, with 5 milliohms at 20 amps, you generate something like 4 watt. And the maximum temperature of the component must be the maximum ambient temperature that you have plus the heat rise. So that means when we offer like a 150-degree component, you would expect to heat the component by 20 degrees, then your ambient condition cannot be more than 130. But this is, of course, a discussion between us and selection, and we can also simulate this. We have a couple of tools where we can simulate the heat rise when we, for instance, get your noise spectrum and we see our impedance against this. I come to this on one of the next slides. And the thermal resistance of the component, of course, because the power on its own is not saying all of the of let's say the power rise because or the temperature rise, because you also have like thermal resistance towards the board. In the copper case, I mean, most of the temperature will be dissipated to the board, and then the board layout, the thickness of the copper, and also the thermal attachment to the chassis may play a bigger role. And may you remember the picture from the last slide, the component on the top side is flat, so that means that it makes it easier that it might be attached with a thermal transition material towards the chassis to cool down or to lose the temperature rise also through the chassis and of your application. And to assign a max component temperature, the plastic material of the choke needs to be selected. We have different materials where we can choose from. The Curie temperature of the magnetic material plays a role because not every material is suitable for high temperature environment, and also the insulation material of the copper wire needs to be selected by your expectations. And in a basic rule, I would say the higher the temperature, the higher the cost of the material. So it needs to be selected properly, that it fits the requirements, but of course not over specified, because then it would bring some unnecessary cost into the application here as well. So a summary of the EMC basic requirements is that depending on the power switching topology, different filtering is required, either over frequency, the level of course, and if it's common or differential mode. The heat dissipation needs to be kept under control, so the DC resistance gives some guidance, but also the real interferences, they will definitely play a role. And if nothing was tested or simulated in terms of interferences so far, it's helpful maybe to evaluate the filter properly by kind of the simulation. So if you have, and I know you have very educated systems in your houses, if you can feed us with a simulation of interferences, it would be even better, because then we can select the material proper. Or when you have made some let's say initial noise measurements or interference measurements, we can go into this as well. So what we usually need on information, call it like a wish list, is like we of course need the ambient temperature and maximum and rated current. We usually get a wish from the customer about the DC resistance, and this is also very valid for us to find the proper solution. Mechanical orientation, of course, is necessary, upright or in a horizontal way. I mean, we have different possibilities, of course, and then an impedance or inductance required. And usually it's specified, or you specify this at around 100 kilohertz, but it could be everywhere. Basically, we just need to value what kind of main disturbances you would accept and how much impedance you need to put against this in this case. Okay, and then the next thing is really we have different behavior of soft magnetic materials. There's some permeability changes over frequency and temperature. There's Curie temperatures, which assign the working temperature. We have magnetic saturation, which is causing the real inductance depending on the interference current of a common mode choke. So I can guide you through this a little bit. I'll give you like a picture. So if we look at the different materials that we have in general, I mean, it's a relatively rough overview here. Then on top of the permeability, there's nanocrystal material. I'm certain that most of you have heard about this. It is on the market since quite a while. However, it is also the most expensive material to choose. But it comes with like 20,000 to 60,000 μ on permeability. And the permeability, of course, assigns the inductance and therefore also the attenuation feature that the material has. Then there's a various lineup of manganese zinc materials, which are from the development coming to attenuate the AM radio interferences or disturbances. So we have different ones there. And of course, for EMC related applications, everyone is looking for very high permeability because it makes components smaller in this case. And we have nickel zinc materials on the lower end. And this is more meant for the high frequency attenuation. So this is kind of a rough guidance, let's say. And this is also like an overview which is valid for all common mode chokes that we do for industrial as well as also for automotive. When we look at the automotive, we narrow this a little bit down. I mean, nanocrystal material is available. It has a high Curie temperature, so it could be used for high temperature applications as well. At the moment, we have a so-called 5HT and 7HT manganese zinc material available, which comes with 5 or 7,000 μ permeability, a very nice saturation behavior as well. And we are working at the moment to increase this up to a level of 10,000 μ. And these ferrite materials are not as costly as nanocrystal materials. That's one of the main advantages. The next one is basically the nickel zinc, and there we have a range of material that we can use for automotive applications. However, this is usually used more in an let's say ferrite kind of way. So that means it's either a ferrite which sits around some cables. It's one turn, let's say, choke, but I give you some kind of idea about this also later on in terms of this as what we have else, what we can deliver in this case. So magnetic components and the material temperature dependence. You can see two industrial materials with this high pickup of permeability before it really drops down. And this is S15H, S18H, clearly only industrial use, and the Curie temperature is somewhere around 120 degrees C, which is okay for an industrial use. And it has good capabilities in this case. But you can see that the permeability is really varying across the temperature, while the materials more on the bottom, the 5H, 7H, 10H materials have not so much variations. And basically, you see inside the green circle, the 7HT and 5HT. These are our new automotive materials. 7HT was just launched this year, and this can keep a very high temperature environment before is really the Curie temperature is coming into play and drops inductance down to zero, or the permeability in this case. But what you see is basically the inductance, but the source of this is that the permeability drops at a certain point of temperature. So then there's another influence, and when you look at this graph, you can see on the y-axis we have the common mode inductance in millihenry, and on the x-axis we have the common mode current. That means that it's the interference current and not the rated current for your application. And what we did is basically we built a choke, common mode choke here in this case, with exactly the same mechanical dimensions, exactly same number of turns, but with a different magnetic material inside. And so you can see the red line is concerning the nanocrystal material, and because of the saturation of that material is not very high, it will drop the inductance very quickly when you really see some noise current or some interference current. So when you look in the middle of the graph, like at around 200 milliamps, it looks like almost all the materials have the same kind of behavior. Sorry. But when you look at the, let's say, zero current, and that is usually what is spec'd in the data sheet because we don't know the interference currents, then you see a big variation. The bottom line here of that slide is that nanocrystalline material behaves very uncertain. So that means when you increase the current, then the inductance level drops down significantly, while using like a ferrite manganese zinc ferrite material, it keeps very stable. And also the just released 7HT is very much more stable than the green line you can see. So it's just on a higher level. And if you compare this, you can also see that with the same kind of shape of a component, you would get something like 40% more inductance because the permeability one-to-one works into the inductance level. And having a look a little bit closer on that, what I just said is it translates 100% one-to-one into the inductance. So the basic inductance formula without looking at the parasitics is really you have like mu0, which is a nature constant. You have the cross-sectioning of the material, so a cut through the core basically, and that's the area in between. You have the number of turns squared, which influence the inductance, but only on the lower level, because when you increase the turns too much, then we'll get a lot of parasitic capacitance, and that drops your effectiveness of frequency to a lower point. And on the low side of the equation, you can see the effective length of the magnetic flux. So that means, let's say the average in a toroidal shape would be the average length of the magnetic flux inside. That's also, by the way, why you see usually chokes which are built upwards, so higher and not so much diameter than a high diameter, because with a bigger diameter, you're losing inductance because the effective length of the magnetic flux will increase, and that makes your inductance smaller. Okay, the influence of the ambient conditions and the power loss. Of course, these are all assumptions, and again, the thermal resistance is not always clear. The DC current creates the heat through the copper. I talked about this, and the noise current creates the heat through initiating the magnetic flux. And when we take a simple example, saying a DC resistance would be 4 milliohm, the current would be 15 amps, then this part of the equation would lead to just below 1 watt of heat rise. But then we have at the 90 milliamps at, for instance, 100 kilohertz, that a customer says, okay, that is roughly our unbiased current, a common mode current that we need to attenuate. And then at that at that frequency, we can see an impedance of something like 900 ohms. That means that there's an additional power loss coming from the disturbances which are going on. And then it sums up to something like 8 watts in total. Of course, it is a rough expectation, only with the main disturbing frequency here at that, for instance, 100 kilohertz, or you may give us, wherever you switch, at 20 kilohertz, 40 kilohertz, but this is usually the highest energy that needs to be attenuated, and from that perspective, I mean, we can have a look and see what roughly the heat rise would be, or what the power loss would be. But I think you also have a good idea about this from your experience in the past in similar applications. Product availability. I mean, we have no standard parts, or let's say catalog parts today available, but we have already created a various of the mechanical standards that we can call it semi-customized. So that means that we have an existing shape of a plastic material with a certain core material inside. We can exchange from 5HT to 10HT. Even some mechanical designs we have, we can put some nanocrystalline material inside, and that is good for smaller quantities. For a full customization, we need something like, let's say, 500,000 pieces per year or something, and of course an application will live 5 to 10 years, because what we are doing when we do a full customized product is we need to set up a complete production line. That is our let's say standard setup in our mindset, that when a choke needs to be fully customized, there will be an individual automotive line which is only producing these kind of product, and it of course needs some quantity. But again, if there is an applicable design which we already created, then it could be used for small quantities, and it might be that in future we are bringing this a little bit differently to the market, and also will have some kind of standard parts available. Let's say a range where you can choose from, right? But this is probably happening then across the next year. Some examples what we did so far, and there's really no difficulty to change, let's say, mechanical designs. We can do them upright, we can do them laying down on the board level, we can use different materials inside. In these cases, I think all of them are specified to 155 degrees C, because it's usually the requirement which is coming from you, from the customer. We are by default making the ACQ 200, of course, happening with all these requirements in terms of vibration resistance and also other robustness features. We can, of course, handle PPAP requests and INDS entries, and the plants we are manufacturing are IATF plants. I mean, predominantly these chokes are coming from our facility in Vietnam, where we produce them, as we need to also always have the cost feature in mind. That should not be that high, and from that perspective, we need to have a low labor cost country, and this is, of course, enabled with Vietnam. And we have a very experienced engineering team in Japan, which are doing all of the designs and which are also doing the samples. So we are very quickly sampling, and to give you an overview about what we, for instance, can do for our customer is like is here. I mean, we have there was a requirement which I cannot disclose with you, of course, but we just said, okay, depending on your space and mechanical space you can provide for the choke. I mean, we can make different assumptions and proposals. I mean, there's you see proposal 1, which is like a choke which is relatively high with 29 millimeters. The others are more flat, 20, 22 millimeters, depending always on the size. But of course, it comes with different kind of behavior, and also different thicknesses of the lead wire. And you can see from the table what kind of possibilities are there. And also with on the left side, the 7HT material, you will find that with a lower inductance, we are able to increase a little bit the differential mode behavior, and that is meant to be because this is kind of the dual mode choke. While on the right-hand side, I mean, we of course have also some differential mode behavior, but you see the distance or towards the rated, let's say, common mode inductance. It is the ratio is smaller here, even if it's on the same level in this case. But you see there, and you need to see that the nanocrystal is of course more expensive than like a ferrite solution in this case. Always to have this in mind, especially for automotive application. So what can we do if the currents are higher? I mean, I talked about things which may conclude somewhere at 50, 60 amps or so, where it's still realistic to do this in a real kind of choke situation. But when the currents go up to more than 100 amps, specifically when you have 200, 500 amps, even up to 700 amps, we had requests already in DC for high power converters. I mean, then of course the classical choke wouldn't work anymore. Also, the production process with bending a bus bar around the core and so on is quite difficult. So in this case, we are more looking into different things, and I show you this on the next slide, just to keep you on the same page. It could be for drivetrain, but also it could be when you have like lower DC voltages and need to drive the same power application. So here in this case, just as one example, say it's like if you have 15 kilowatt, I mean at 400 volt, you will have like a current of 37.5 amp. But if you want to have the same application power at 48 volts, I mean, then you easily go above 300 amps, and then you need a different solution. And in this case, it's possible to put bus bar ferrites together, also pretty customized, and they can also be differential mode if they are just around one bus bar. They could be common mode if they are concluding both bus bars and a big air gap in between, or they can also be dual mode because we can lower the air gap, as I showed on one of the first slides, just to increase a little bit the magnetic flux around the single wire or the single bus bar, then you get like a dual mode behavior. And if you just look into this, it's just the one choke, just the one turn choke, nothing else. And one example, and we simulated this, is like this kind of mechanical layout. And you see the two noses of this double E core. And if you put the noses together from them, more together from the mechanical design, then you would increase the differential mode inductance. If you put them more apart from each other, then you would shrink it. But of course, you need to have always the saturation also in mind, as I also lined out in the beginning. Here in this case, we took 5 HT, and you see the certain dimensions in millimeters. And we can simulate what basically is then in terms of resulting inductance over, let's say, the DC current. On the left case, it's really the rated current. On the right side, it's the interference current, which may happen. And I mean, if you go above 1 or 2 amps on that level, I mean, then anyway, you have some different problems that you need to fix in a different way. Of course, also in this case, you will have probably some DC link capacitors, something like this, which will also attenuate the differential mode noise. And you also probably will have some Y capacitors which help with the common mode noise. But this is all like a filter in total. Okay, and that's almost the end. The only other thing I want to kind of highlight here is that, of course, these are not the only components we can deliver for automotive applications. We have 4 main areas we're looking into. There's like traditional, let's say, power inductors, SMT ones usually, which we are also doing. And in the power and boost side, so when you really need a lot of power, there we have even bigger kind of mechanical designs. We have some magnetic slurry solutions like this one where you see the 50 kilowatt on, which is like a big boost inductor for the drivetrain, which can withstand a couple of hundred amps if you need to bring the voltage level up from, for instance, 48 volt to 100 or 200 volt, or also from 200 to 400, whatever you do. And then we have the ferrite chokes, which are also incorporating sometimes nanocrystal material, depends on the requirements from customers. And last but not least, we have flex suppressor sheets, which are for very high noise attenuation. So if you are above 1 gigahertz or in a range of 800 megahertz or so, that is a very effective material. Also, we have their automotive qualified version and the ferrite cores, of course, for kind of very, very high power applications. And that's what I want to put together for you. I thank you very much for listening, and I think Alex comes back now with questions, I think so.
Yes, Michael, thank you for presenting. It was very interesting, and I can see many questions from the audience. So thank you so far, but still we are open for your questions. So please put your questions in the chat window on the right-hand side, and then I hope we can all answer now. So the first question is, do we offer 1200 volts DC parts for heating system in EV applications?
Yeah, that's no trouble. I mean, we can define and design according to an application voltage. By default, we have an isolation anyway of 2400 volt AC, but with 1200 volt, there's no trouble. So far, we haven't had so many requests there because the semiconductors have some limit as well. I mean, when there's something, they just, the one who asks this question should just come to us. You can see also my contact details here. We have field application engineers everywhere in Europe and also salespeople, which can guide you in that way. And I can discuss this with our engineering team in Japan.
Okay, because I received also more details like peak current, RMS current, and switching frequency, but we agreed we can have later contact after the call. So thank you. So far, we will contact you. Okay, perfect. Okay, I just read contact. Okay, the next question is, can you roughly explain the difference between AC and DC line filter?
Yeah, I mean, in general, there's not a big, it's not a big impact. The only thing is sometimes in an AC application there are different requirements. So that means that we have different voltage levels. But in general, an AC and DC choke is almost, from the construction method, it's the same. We do this, for instance, and it's a good point, because we're not only doing this for the DC high voltage applications, but also when you have charging applications like onboard chargers and such. I mean, we do also, of course, AC design as well for Delta, as also for star connections. And this is then really the difference in terms of voltage behavior, and also in terms of how many coils we need to put around a certain choke, because in a Delta we have to do 3, and in a star connection we have to do 4, because the neutral needs to be filtered as well. But in general, there's no, instead of selecting materials probably, but I mean the general design is more or less the same.
Okay, thank you for this answer. So if there is more question, the person who asked can contact me today later if needed. The next question is, do you have SMD common mode chokes?
No, not at all. I mean, we have a few, to be honest, in the DC common mode chokes, but this is more like for 50 volt and low currents and so on, and not at all automotive qualified, because as I said before, we have more we need to build a line for this one specifically for a certain series if we want to do this automotive graded, and we don't have this because the development was coming more from the communication area. But so far we have decided against this. It could be that we will maybe develop this in a few years, but it is not on our, let's say, roadmap at the moment.
Okay, and the final question for now, it's a very interesting question. Can I use a common mode choke for differential mode by only using both windings in series or parallel? I don't know why this is the question, but it's an interesting question.
Yeah. I see this. I saw also data sheets from other suppliers, which are stating that they can be used either in a common or in a differential mode way, just by changing, let's say, the board layout slightly, that you put them in series and in the same direction. I mean, the problem is usually the material, and it comes to the saturation. So when we propose, and we also have pure differential mode chokes in the automotive area, we have usually a kind of what people call the amorphous iron. So it's basically an iron powder surrounded by a silicon shell that gives a distributed air gap, because the saturation of these materials is way higher. So we talk about something like 1.7 Tesla in saturation, while a manganese zinc material has only half a Tesla, roughly, like these two materials, 5HT, 7HT, what I talked about, is in the range of half a Tesla on saturation capabilities. So as I lined out on one of the slides, if you reach the saturation, then you will see declining inductance or declining permeability, because you reached already the point where you can't magnetize the material more than you did before. On the other hand, you have, of course, core losses, which can go to infinite. And that's the reason why the problem really from that perspective is, I mean, yes, you can use it, but I don't think it makes a lot of sense in this case, because usually, as I said, we have a series called SHBC, I believe, which we are doing in automotive versions as well, but this is a completely different material than I have just discussed here before.
Okay, I just received another question, interesting question. Do we offer information about the complex permeability in the data sheet? Because currently this is not available in our data sheets.
Yeah, in the moment not. I mean, I know where this kind of question is coming from, because, I mean, you have like mu prime and mu double prime. And mu double prime are the losses, while mu prime is inductance. That is what is usually more needed in power inductors, so differential mode chokes or power inductors. But because it needs to somehow store the energy. I mean, mu prime is really the inductance where what you need for PFC stages or something like this, to store the energy for a short moment until you bring it in the right timing position with the voltage again. While the mu double prime, the core loss basically is what you're looking for in EMC predominantly, right? I mean, there's a couple of other things which are around there. In the data sheet so far, we have not done this, but I have when I get requests, I get this basically from my development team in Japan. They can share the curves with us, and on demand, I mean, we can share this, of course, also with the customer. So if you're interested in this, I mean, the 5HT I have on file, the 7HT, I think I can request, and for the nanocrystal material, I think we can measure this as well. I mean, this should not be a problem.
Okay, thank you. So for the moment, this seems like we have answered all questions for now. To all attendees, thank you for joining today. Please feel free to answer questions to your local FAE, to Michael Freitag, or to me directly. We can answer all of your questions also later, or to your local sales contact. And just for information for the German people or living in Germany, we have in the next weeks our KIT seminars. Please go on our engineering page if you are interested. We still have a few places open, so please be fast to get one of the last seats. The seminars are for free. It's a full-day seminar tomorrow in Frankfurt area, on Thursday in Eindhoven. So everybody who wants to join, it's free, and also the lunch is for free. So at least you get a free lunch. Okay. Thank you, Michael, for presenting today, and hope to see you next time.
Thank you, Alex, for being the host, and thanks for the audience. I mean, without them, I mean, it would be not a good idea to have a webinar, right? So
right.
Most of the thank is in regards to our audience, of course. Have a great day.
Okay, goodbye.
Goodbye.